Welcome to the deep dive. We're here to give you that well-informed shortcut, really digging into the latest science. Today, we're tackling myopia control. It's a huge topic. Specifically, we're looking at some brand new research comparing two ways to slow down eye growth, these highly aspherical lenslets, HAL, versus a strong, simple defocus lens.
Right.
Our mission to see if this, fancy new HAL tech can trigger the same immediate protective response inside the eye is a really straightforward, powerful approach.
Yeah, and to get this, you really have to grasp the basic problem we're fighting. Progressive myopia is essentially the eyeball, the axial length, or AL, getting too long. And the weird thing is, traditional glasses can sometimes make it worse peripherally. They can cause light to focus behind the side parts of the retina. That's hyperopic peripheral defocus,
Yep.
HPD.
So HPD is like the eyes go signal, grow longer.
Exactly. It's like the eye thinks, oh, I need to reach that light back there. Let's grow. So the whole game now is to flip that, create myopic peripheral defocus, light focusing in front of the peripheral retina.
The stop signal.
That's the idea. The stop growing signal.
And the way researchers are checking if that stop signal is actually working, like right away, is by looking at the subfoveal choroidal thickness, SFCHR.
Precisely. SFCHR is the immediate biomarker everyone's watching. The theory is myopic defocus makes the choroid, that's a layer rich in blood vessels right behind the retina, it makes it thicken up almost instantly.
Okay.
And this thickening physically pushes the retina forward a tiny bit, which effectively shortens the axial length. It's like the eye's first line of defense against getting longer.
The choroid thickening is like the body pulling the fire alarm.
Okay, so this study we're diving into, its specific goal was to see if HAL lenses could pull that alarm in just, 90 minutes?
Yep, 90 minutes. And comparing it directly against a known heavy hitter, a simple +3 diopter full field defocus lens, a really strong signal.
All right, so we get the theory, peripheral myopic defocus stop signals. But how do these actual lenses, the highly aspherical lenslets, the HAL lenses, how do they actually do that? It sounds complicated. They are pretty sophisticated, yeah. Imagine a contact lens. It's got a clear central part. That's your normal distance vision. But around that, 11 rings, continuous concentric rings packed with tiny, tiny lenslets, each about 1.1 millimeters across.
11 rings of lenslets. Wow, what's the point of all those?
Well, they're not really for seeing clearly in the periphery. Their job is to specifically manipulate the light focus. The manufacturer's idea is that they create this, they call it a volume of myopic defocus image. Think of it as a 3D shell of stop signal light that sits about 1.2 millimeters in front of the retina, bathing the periphery in that signal.
So it's not just like adding a bit of plus power out there. It's a structured, almost like engineered signal shape, designed to be deep and cover the right spots.
Exactly. It's about the shape and depth of that defocus volume. And look, this isn't just theoretical anymore. We've seen results from 2-year trials. HAL lenses genuinely slowed down myopia in kids compared to regular single vision lenses.
By how much?
Pretty significantly. Almost a full diopter less progression in prescription. And axial elongation slowed by 0.41 millimeters. That's meaningful.
And you mentioned something about the choroid long-term, too.
Yeah, other data shows that over 3 years, they help prevent the choroid from thinning, which you'd normally expect in progressing myopia. So it suggests that protective mechanism we talked about, the thickening, might be sustained or at least counteracted thinning.
Which makes testing this immediate 90-minute choroid response even more critical. We want to see if that initial trigger, that fire alarm, is actually pulled effectively by HAL. Okay, so to tough that immediate trigger, they set up this head-to-head comparison. Walk us through the experiment. Who is in it?
Right, so it was a prospective study. They recruited 25 young adults, ages 20 to 30, mostly students probably, with sort of moderate myopia. Average prescription was around -2.25 diopters.
Hold on. Young adults, ages 20 to 30. But HAL lenses are meant for kids, right? To stop eyes from growing. These adults' eyes have probably stopped growing years ago. How relevant is a biomarker response from a stable adult eye?
That's a really fair question. And the researchers knew this was a limitation. They specifically chose young adults mainly for, compliance. Getting really precise, frequent measurements of choroidal thickness and axial length needs someone who can sit still and cooperate perfectly. That's just, frankly, easier with adults than young kids.
Okay.
So you have to see this study more as a mechanism check. Does the lens generate the signal the way it's supposed to? Does the physiology respond immediately as predicted? It's not directly proving it works long-term in kids, but validating that initial biological step.
Got it. A mechanism check, not a treatment trial. So what did they actually do with these adults?
It was a neat setup, a crossover design. Each person came in twice, with at least 5 days between visits, that's the washout period, letting any effects from the first lens disappear. On one visit, they wore the HAL lens in their dominant eye. On the other visit, same eye, they wore the strong plus 3.00D full-field defocus lens.
And the other eye.
The non-dominant eye wore just a standard single-vision contact lens, their normal correction. That served as the control eye for that person, which is great for accounting for just, natural changes happening in both eyes.
Makes sense. And what were they doing for those 90 minutes? Staring at a wall?
No, a bit better than that.
Yeah.
They watched a movie. It was projected about 6 meters away, so distance viewing. And the room was kept pretty dim, about 10 lux. The idea was to make sure the main visual input driving any changes was really coming from the contact lens itself, not bright room light or complex near tasks.
Right, and the measurements were taken when?
3 key times for both eyes. Right at the start, baseline. Then after 60 minutes of watching the movie, and again at the end, after the full 90 minutes, they were measuring axial length, AL, and that crucial subfoveal choroidal thickness, SFCHR.
Okay, finally, let's get to the results. The big question. What happened to that choroid thickness? Did the sophisticated HAL lens manage to trigger the thickening like the simple strong plus 3D lens?
Yes, it absolutely did.
Yeah.
That's the headline finding here. Both the HAL lens and the plus 3.0D defocus lens caused a statistically very significant increase in SFCHR compared to the baseline measurements. P-value was less than 0.001. So the mechanism fired up.
How much thickening are we talking about?
Okay, numbers. After the full 90 minutes, the plus 3.00D lens, the sort of brute force method, increased SFCHR by an average of 7.36 micrometers.
Right.
The HAL lens, the more complex peripheral signal one, increased it by 6.62 micrometers.
Wow, okay. So 6.6 versus 7.3 micrometers? That's
Right.
surprisingly close, isn't it? Considering one hits the whole eye and the other is just the periphery with a complex pattern.
Exactly. That's the really interesting part. While the number for the plus 3.00D was slightly higher, the difference between the two interventions, statistically speaking, was not significant. The p-value comparing them was 0.595.
So basically, the HAL lens achieved pretty much the same immediate choroidal thickening response as the really strong full-field lens. That's a big win for the peripheral defocus concept, right? Validating that approach.
It really is. It strongly supports the idea that you can trigger this key physiological response just by manipulating the peripheral optics and do it almost as effectively in the short term as a very strong full-field signal.
But you mentioned something earlier about a plateau. Did the thickening just keep going for 90 minutes?
No. And this is also quite interesting. The thickening happened fast, but it seemed to level off. When they looked at the timing, they found a significant jump in thickness between baseline and the 60-minute mark for both lenses.
Okay.
But between 60 minutes and 90 minutes, no further significant increase. It sort of hit a ceiling around the 1-hour mark.
A ceiling? Why would that happen? Is the choroid just, stretched out as much as it can immediately react?
That's a good way to think about it. It suggests there might be a limit to how much the choroid can acutely swell in response to this kind of stimulus. It reacts quickly, but maybe that initial rapid thickening phase has a cap. It doesn't just keep getting thicker and thicker indefinitely in that short window.
That has implications for long-term wear, maybe. Like you get the initial boost, but then what?
Potentially. It hints that maybe the long-term success isn't just about this initial rapid thickening, but perhaps other slower mechanisms or maintaining that signal consistently. The plateau is definitely something to think about.
Okay, so the choroid thickened beautifully with both lenses. That's the fire alarm. And the whole point of that thickening is supposed to be that it pushes the retina forward and makes the eye slightly shorter, right? So did the axial length, the AL, actually change? Did the eye get shorter?
Well, this is where things get a bit less clear-cut, or maybe anticlimactic. Despite those really clear, significant changes in the choroid thickness, there was no statistically significant change in axial length detected for either the HAO lens or the plus 3.0D lens over that 90-minute period.
No change at all, even with the choroid swelling up by 6 or 7 micrometers.
Pretty much. The average change for HAL was basically 0, like 0.000 micrometers plus or minus a standard deviation. For the strong plus 3.00D lens, it was a tiny, tiny average shortening of about 7.6 micrometers. But the variability was huge, and it wasn't statistically significant. Essentially, within the noise of the measurement, AL didn't budge.
So the mechanism, the choroid thickening, worked, but the expected consequence, the eye shortening, didn't show up in the data.
Correct. And because the AL didn't change significantly, they couldn't find that expected negative correlation. you know, where more choroidal thickening should directly correlate with more axial shortening.
Yeah.
The AL data was just too flat.
Why would that be? If the choroid swells 7 microns, shouldn't the AL shorten by roughly 7 microns? Is 90 minutes just too short to reliably measure such a tiny AL change? Or is the relationship more complex?
The most likely culprit is probably the measurement challenge over such a short time. We're talking incredibly small changes. Axial length measurement, even with precise instruments, has some inherent variability. It's possible, even likely, that tiny shortenings were happening, but they were just too small to reliably detect above the measurement noise within only 90 minutes.
Okay, so the effect might be there, but just too small to see clearly in this snapshot.
Probably. It highlights how sensitive these measurements are. It's also worth noting, though, that they did confirm the standard baseline findings. People with higher myopia in the study did tend to have thinner choroids and longer axial lengths to begin with. So the underlying relationship between these structures over the long term is definitely there, as expected.
All right, let's try to synthesize this. What's the big takeaway here? It seems the HAL lens passed the first test. It triggered that immediate choroidal thickening, matching the effect of a really strong defocus lens. That validates the mechanism, right?
Yes, I think that's the primary positive finding. It shows that the peripheral optical strategy employed by HAL does effectively engage that initial physiological response pathway. It supports the idea that choroidal thickening is a key part of the picture for how these lenses might work.
But we need to circle back to those limitations we discussed, especially using adults.
Absolutely, we have to be cautious. This study used adults, 20, 30 years old, whose eyes are largely stable. HAL lenses are mainly for kids whose eyes are actively growing and potentially much more responsive, more plastic. So seeing the signal trigger in adults is good, but you can't just assume the long-term growth slowing effect will be identical in children based on this alone.
It's a proof of concept for the signal, not proof of efficacy in the target group. What else?
The other point was that potential diurnal variation. Remember, appointments were spread between noon and 4 p.m. Axial length and choroidal thickness naturally fluctuate a bit during the day. While using the other eye as a control helps account for this, having that wide time window could introduce some noise, especially when looking for tiny changes.
Right. And then there's that axial length puzzle, no measurable change. Does the fact that the complex, fancy HAL lens didn't perform better than the simple, strong +3 lens in triggering the choroid raise questions? If the immediate response is the same, why the complex design?
That is a really interesting point, and it leads to bigger questions about how these lenses truly work long-term. We know from clinical trials that HAL and similar complex lenses are effective at slowing axial elongation over years.
Right.
So if their immediate choroidal thickening effect isn't dramatically different from a simple defocus, maybe the long-term success isn't just about the amount of immediate defocus or just that thickening. Perhaps it's related to other optical effects, like how these lenslets change higher-order aberrations across the retina, or maybe they alter contrast perception in a way that sends a different kind of sustained stop signal.
So the immediate choroid bump might just be step one, and the real magic of the complex lenses lies in something subtler or longer acting.
That's what seems plausible. The long-term efficacy is proven, but the precise mechanism beyond just peripheral myopic defocus causes choroidal thickening might be more nuanced, involving these other factors that play out over time.
Okay, wrapping this deep dive up. What we've learned is pretty significant. Even in a very short 90-minute window, these sophisticated HAL lenses do trigger that critical protective response, the choroidal thickening. And importantly, they do it with basically the same immediate power as a very strong full-field defocus lens. It strongly validates the principle that manipulating peripheral vision can kickstart this process.
It does. But now for that final thought to chew on. We saw the choroid thickens quickly, but seems to hit a plateau around 60 minutes in this study. We also know from other research that these defocus effects can be reversible. Take the lens off, and the choroid might thin back down relatively quickly. So if that immediate thickening response is both capped in magnitude and potentially transient, it raises a really big question for you to consider. What other mechanisms must be at play for lenses like HAL to achieve the significant lasting reduction in eye growth that we see in those multi-year clinical trials with children? If the quick choroidal swell isn't the whole story for long-term control, what slower biochemical signals, perhaps changes in retinal gene expression or scleral remodeling cues, are being triggered by these lenses over months and years to really put the brakes on axial elongation?
So the immediate response is real and validated, but the path to sustained long-term control likely involves more than just that initial bump.
Exactly. That's the next frontier in understanding how these truly work.